Thank you. Good afternoon, everybody. It's my distinct pleasure to introduce Professor Andrew Lamperski to present his work on non-convex learning, system identification and stabilization for model-free reinforcement learning. Andrew joined the University of Minnesota in 2014 as an assistant professor in ECE. And basically, before that, he received his bachelor's in biomedical engineering and mathematics in 2004 from Johns Hopkins, and a PhD in control and dynamical systems 2011 from Caltech. He has held many prestigious positions, including as part of the Whitaker International Program, a postdoc position at University of Cambridge. And his research interests include optimal control and machine learning with applications to neuroscience and robotics. So without further ado, Andrew.
All right, sounds good. Thank you very much. All right. I'm going to mute myself. How about that? All right, yeah, easiest thing in the world. Okay, so let me get that. And should I do that? All right, so here's what I'm going to do. Events, soft.pdf. And as we have just discussed, the videos are not going to load, and that's all right. I'll gesticulate what they should be doing. I could like play them, but that's kind of a bother. They're on my computer. Please let me find the right window here. All right, so I'm sharing this guy, and then I'm gonna put it up into presenting as a slideshow. All right, awesome. So let's get rolling. All right, so yeah, as I said,
looks like you see your. I'm not seeing the slides change or anything like that.
Really? Yeah. All right, so I'll stop the share and I'll.
I think we're a little bit behind.
There's just a little bit of a lag. All right, so I'll just try to go real slow. So yeah, I'm Andy. Just a little bit of ground rules before we get going here. I like to be interrupted. Because one of the things that is true is I don't know most of you. Okay, so I don't know what you do know, and I don't know what you don't know. And so I put things in here that range from really basic to like really out there. And so, if you want clarification on something, just stop and ask me, and I'll give you that clarification. I don't mind if it makes me spend more time on one piece than another piece of the talk. Really, it's totally fine by me. So I actually really like it. So just keep that in mind, so that if you see something, you're like, what is he talking about? He's being a ridiculous person. Just ask me, okay? Or stop me and holler or whatever. It's totally fine. So, as briefly mentioned in my abstract of a title, I'm going to be talking about things about handling non-convexity in learning and system identification. And I'm also going to be talking about how do you stabilize systems without actually learning a model. All right. Cool. So this first work, this is work with my student, Yuping Zheng. Just fairly recently got started on this, but it's fun stuff. So just as a quick background and introduction to what I'm going to talk about, I'm going to talk about essentially machine learning in a nutshell. Like, what is it? What do we do? And why do we care? So and maybe at this point, this might be a time for me to let you all, reduce your expectations even a little bit further. This is going to be a theory talk, so there's not going to be a lot of cool stuff flying around or driving around. And I had a few simple toy videos, and even those didn't load, so you won't even see that. Yeah, so it is going to be kind of a theory talk about things that are, they're all related to what we do in robotics, but it's not robotics itself. So just keep that in mind. So regression in a nutshell, what we got here is we're going to get data. We've got input-output pairs, X and Y, X and Y. So here we've got the X-axis, we got the Y-axis over here, and we get a model. We're going to say, I'm going to say, maybe try to fit a line to that data, or maybe I'll try to fit a neural net to that data. Well, how do I fit that line to that data? Well, I take my model and I plug it into a loss function that says, how well am I actually using the input to predict the output? That would be a standard thing you would do in learning for regression, learning with neural nets, and so on. You plug your data into the model, and then you put that into a loss, and then you minimize that loss, and you get a fit. All right, cool. So that's regression. Awesome. So there are some challenges, though. I mean, it's really easy to state what this is, but actually doing this in practice has some difficulties. For instance, one that we're going to talk about a lot today is non-convexity. So there's convex functions, and convex functions, you've just got one minimum. Okay, so you run any sort of off-the-shelf algorithm like gradient descent or Newton's method, whatever you have, you're going to get to this minimum, and there's nowhere else you could go. With a non-convex function, we got a lot of minima, right? There's a minimum here, minimum here. If we looked at the function further out, there'd probably be more minima other places. So a lot of the off-the-shelf algorithms that we have are going to get stuck in these minima, and we're going to talk about that a lot. And another issue that we have is generalization. So when we're doing machine learning, we have data, and we learn our model based on the data, but we don't care just about fitting the data. One of the things is we want to predict the behavior of new data. That's the power of machine learning, is to be able to make predictions on, say like the stock market. Oh, these stars are going to do great. That's a winner right there. You want to be able to predict what's going to happen into the future, given the data that you have. You want to be able to predict new data. So these are just, that linear function fit to some data, and you can't really see it that well here, but we've got a few training points, and they kind of look, when you go back here, this line looks pretty reasonable. And this, like, what is it? It kind of looks like, what is it doing? But it turns out that in this case, there actually was a lot of structure, and the neural net was picking it up. And so in this case, the neural net actually generalized really well, even though it didn't look ahead of time like it should. But there's no immediate guarantee that the neural net would generalize really well. But in this case, it did. And then the other issue that we have a lot of times is that the data sets that people use, especially these like large tech companies, are just massive, right? You just think about like, trying to learn from the entire database of Facebook users or something like that, right? It's everybody's mom in there, right? You gotta learn a lot of stuff. And so, so this could be huge, so big that you just can't even evaluate this function, right? Like you just simply writing down this value would just take forever to write it down. So, yep. And what we're going to talk about today goes even a little bit of a step further here, because we're going to talk also about how do you do a lot of these regression type problems in the case of an autoregressive model. So an autoregressive model is kind of, regression is built into the name here, really is kind of a special case of regression. But in this case, we're doing it with a time series. So we're still trying to predict from our inputs what our output is. But in this case, the inputs that we have to our regression model actually are pieces of history, right? It's previous measurements, it's previous inputs we might have given to a dynamic system. And this is one of the core problems in system identification for dynamic systems. So if you have a physical system, you're putting inputs into it, you're trying to predict what are you going to measure in the future if you're going to put these inputs into it. So this is, again, a regression problem. So it really is just like what we saw before. The main difference here is that there's a lot of correlation over time. So if you look at this time series, this would be this might be the measurements, and these might be the inputs that we're putting into the system. You could see that, hey, these U's really have a lot of correlation over time, and these Y's really have a lot of correlation over time. It's not just jumping arbitrarily across the whole space. It's very correlated. And so this actually makes a lot of the analytical things that we might do for the analysis of regression algorithms harder, because a lot of the classical analysis of regression algorithms assumes that the data is independent identically distributed, or IID. And so just a little wrinkle here, we're going to be dealing with both cases in this scenario in sort of one go. So the main workhorse behind most of machine learning, and definitely all of regression analysis, is stochastic gradient descent. Like, that's what people do. And so stochastic gradient descent, it is this algorithm right here. So we can look at it right here. We've got the current parameter, And we see how we make the next parameter by taking a gradient in the direction of our loss function for one particular data point. Okay, so we're not using the whole data set, we're looking at one data point. There's of course lots of variations. You could use mini batches and so on, like tons and tons of variations on this thing. But this at its core is the basic stochastic gradient descent algorithm. And the thing that's great about it is it's really scalable, right? You can apply this to really, really massive data sets because you're only looking at, one sample at a time. You don't have to wait for the entire data set to come in to go and use this. And gradients are really easy to implement computationally. So you can do this for very, very big models as well. So if you can chuck a really huge neural net model into here and apply it to a really huge data set. And yeah, I mean, you might not be able to get full cover. You might not be able to sweep through the whole data set efficiently, but you can get something useful out of it pretty quickly because of the fact that the individual iterations of this algorithm are very, very efficient. And so, we got lots of variations, and then there's just a lot of software to do it because it's such a valuable thing. Just tons of people have implemented it. You've got TensorFlow and PyTorch and all these things that just have off-the-shelf, very good implementations of this algorithm. And of course, there's the one con that we alluded to before, which is, of course, it can get stuck in local minima. And there's not great analysis of well, where's it going to get stuck? What's it going to do? And so on. That's still, a fairly fuzzy thing. Especially when you start dealing with general loss functions. So enter the Langevin algorithm, which is what I'm going to be talking about for the first half of this talk today. So the Langevin algorithm, if you kind of look at it, well, that's just gradient descent, except we've got one other piece, which is IID noise. And we're just going to put Gaussian noise on it. So, it is essentially no harder to implement than standard gradient descent, because you're just taking IID noise of the same shape and dimensions of your parameter and just adding it to it. And then we've got this temperature parameter here. And we're going to see what that temperature parameter does later on in the talk. But essentially, it's going to control how much noise you're putting into the system. You can really see that. If this beta is big, you're not putting in much noise at all. So that would be beta big corresponds to a low temperature thing. So you're not really doing something. So the reason I'm saying things like temperature and so on is this equation was originally described in physics. And so this was a stochastic differential equation from physics that people would talk about. And they really were talking about things like temperature and so on whenever they were dealing with these. Yeah, this basically controls how much noise we're putting into the system. And so this was long ago recognized that you could do stuff like stochastic gradient descent with this. And this should allow you to escape from local minima, get around saddles and all this kind of stuff. And that was sort of argued that this should happen for quite a long time. And in the last, say, 4 years or so, a really nice quantitative theory about how this actually works has emerged. And so this really does, this noise that you put in really can enable you to escape from local minima, get to the global minima, and so on, as long as you're tuning this temperature parameter correctly. But of course, okay, I don't want you to get your hopes up too high. This is for non-convex optimization. And what do we know? So I'll ask, this is a class, right? Is this a class technically? It's an economic?
It's the first cohort.
Okay, so good. So I'm going to ask you a question. Quiz. Why, what do we know about non-convex optimization that makes us believe that there would be no algorithm that would allow us to solve it in general, efficiently, solve it efficiently? It is, kind of sounds like NP hard. NP hard, yeah, it's NP hard. So non-convex optimization is an NP hard problem, meaning that essentially, it's really, really unlikely that we're ever going to find an algorithm that will just solve it all, okay? And so we're going to see that, yeah, if you do this, you can escape from these local minima, but it might take a very long time. And this very long time depends on the properties of your the parameters of the system, and in particular, the properties of this function is going to kind of dictate when this actually allows you to escape efficiently and when it doesn't. And so somewhat more recently, there's been extensions to correlated data like we talked about for this autoregressive processes. And there's a lot of other applications, right? You could do this for optimization if you just had no external data in there, just a standard optimization then. And the other thing that's kind of neat is you can do this for Monte Carlo sampling, and you can use this to sample from arbitrary probability distributions. So that's another kind of neat thing that comes out of this. So we'll talk more about those in a little bit. But one of the main limitations of the current analysis and what I'm trying to address is that almost all of the current analysis, including all of the analysis for non-convex problems, focuses on the case of unconstrained problems. So meaning that we've got the parameters can just take any values in Rn, right? Any real numbers that you want. But constraints arise a lot, right? In a lot of applications, like, you know, in machine learning, a lot of times we put constraints on our parameters to ensure numerical stability. Basically, we say, okay, if the parameters are getting too big, just clip up to a box. You know, just clip the numbers into some finite region so that we don't induce a lot of numerical errors. And then in optimization, of course, like the constraints are just come from the problem, right? Like if our goal is to design inputs to a dynamic system using optimization, but we have a maximum force that we can apply, well, that would be a constraint coming from this real world concern that, hey, there's only so much force we can apply in our system. So that's just a hard bound on what we can put there. And then whenever it comes to probabilistic sampling, we're not going to go too much into it, but a lot of probability distributions, their support is naturally limited. Like if you're trying to search over the weighting, the relative weighting between a bunch of objects, then that weighting has to be an actual probability distribution, which means they have to sum to one, they have to be non-negative. These are constraints. So in a lot of cases, just constraints are natural, but the theory of that is super limited. So tons and tons of theory on how to do non-convex losses for unconstrained problems, some amount of theory for convex losses and convex constraints, and then just this like little tiny and not quite applicable thing of non-convex losses over Riemannian manifolds. But for a lot of the practical things we want, it's not there. The theory is not there. So that's what I'm going to talk about. Yeah.
If you can analyze the unconstrained problem, so can't it be boiled down to a constraint? Why does it not apply for the constrained environment actually?
Yeah. So yeah, it turns out that it's fairly non-trivial, and we'll get to the reason as to why. Essentially, the analytic techniques become very different, and like very different, but different enough that like people didn't figure out how to do it. Okay. Right. So this is the algorithm that we're going to talk about. So as it turns out, it's really easy to do it in practice. It's the analysis that's hard. So the practical algorithm is just one little tiny step beyond what we did before. Namely, we're going to do a projection. Okay, so we're going to take this stochastic gradient descent with some additive noise, and then we're just going to project it. So just like when I talked about with machine learning, if our parameters exit a set that we care about, we just bring it back in. And in the assumptions that we have in this problem, the main thing, it's smooth, so it's got, you know, well-defined continuous derivatives, but it could be non-convex. And we're going to look at a convex compact constraint set. So it's a bounded constraint set. Nearly sure we can extend this to an unbounded constraint set, and I'll kind of discuss a little bit about that later. But for now, we're going to deal with a bounded constraint set. And as I said, this particular algorithm, with the case of no external noise and a convex loss, which is a much easier case, was handled in a paper from a few years ago. All right, so just a preview of what we're going to talk about is, if we've got that algorithm, we can get a really precise bound on what the iterates do in terms of what's called the Wasserstein metric, okay? The Wasserstein distance. So I needed to just describe a little bit of notation here. So I'm going to have this loss function that kind of takes our original loss that we had and says, this is what happens when you average out the external data. This in machine learning parlance would be what's called the population risk, okay? So this is what happens if you actually average out the data. And of course, we don't know what that probability distribution is, so we can't actually compute that average, but that's what it is. And then this is what's called the Gibbs distribution, restricted to that constraint set, otherwise sometimes known as the Boltzmann distribution. So it's just raising this the exponent. And you notice here the beta from here is that temperature, and it kind of controls that piece over here. It kind of controls how peaked the distribution actually is. And our main result is that when we iterate our algorithm, This corresponds to the distribution of the iterates. This is the law of the iterates, or the probability distribution. We can bound how close that probability distribution is to the Gibbs distribution. And we see here is we've got a piece that is decreasing exponentially as the iterates go up, and a piece that is growing slowly, logarithmically, as the iterates go up. And so what happens is because this decreases so much faster than this, by a careful choice of our step size parameter or our learning rate, we can actually make our Wasserstein distance go to 0. In particular, go to 0 at this rate of t to the negative 1/4 times some logarithmic factors. So that's sort of the main result here. And I'll just a little bit more detail go into some of the applications that we can do with this. So it turns out that if we had an arbitrary probability density over that set, so this could be the posterior that you're taking after having observed a bunch of samples, which that's a common problem that you have if you've ever done filtering. You have a bunch of data, you have a bunch of samples, and you want to compute the posterior distribution. And unless you have like a linear Gaussian system, that is typically an intractable inference problem. You typically can't compute that posterior exactly, but sometimes you know it up to a constant factor. A lot of times you know it up to a constant, you know it up to a constant factor, namely you know the joint distribution of the likelihoods and your priors. And what this allows us to do here, by just careful choice of what we put our loss function as, it turns out that our Gibbs distribution is exactly the distribution that we want to sample from. So, so that's a nice little thing, and you don't have to do any of this extra stuff that people do in Monte Carlo sampling, like taking metropolis steps and so on. And then the other nice thing for machine learning and for optimization is we can actually tell you very precisely how to tune these parameters and how long to wait, so that you are within a factor of epsilon of the optimal solution, even for a non-convex problem. So the magic here, okay, like this bound isn't good, and you wouldn't expect it to be good based on what I said before, because it's an NP-hard problem. But the kind of beauty of it is that, hey, with just minimal effort beyond standard stochastic gradient descent, I know I will actually get to the global minimum. Just might take me a very long time, but it's not that much extra work, and it'll look mostly like stochastic gradient descent the whole time. So, you know, it's not that basically, yeah, you know, from a practical level, you wouldn't necessarily get there, but you know you will, and it's not hard. So why not? Why not add a little bit of noise? And this would have been me showing how you could do SLAM with this algorithm. So simultaneous localization and mapping. Inside a little video of it. Basically this is a trajectory, and these were some beacons, and you're gonna try to localize yourself and figure out where the beacons are. But the video didn't load, so no, sorry. Like I said, I'm serious. It really was looking good on my computer. I'm not lying to you. Other people saw it. I gave a talk. I gave this talk like 2 months ago, and it loaded there. All right, ask the people who went to Colt. They saw it. All right. All right. So just a real quick thing, and maybe I might. What time should I end, by the way?
Usually have about an hour allocated.
Okay.
Give or take a little for 2 minutes.
All right. So here's I'm gonna skip this. I put this in. This is kind of a highly technical piece. I don't think I need that in my life right now, because it's fine. All right. So this is the main result, sort of stated more precisely. What are the precise assumptions and so on. So if ZT is a stationary in what's called an L mixing process, and I'll tell you a little bit of what things are L mixing. So an L mixing process is, so mixing processes more generally are stochastic processes where the correlation and the probabilistic coupling between the variables decays over time. So if I look at the data from this time and the data from this time, if the gap between them is long enough, they're nearly independent. Okay, that's what it means to be mixing. And so there's tons of ways of defining mixing processes, and L mixing is one that is particularly good for system identification. All right, so a simple thing that is L mixing is anything that's IID. If it's independent, identically distributed, then yeah, each step is independent and it is automatically L mixing. But a more interesting case is if you had any kind of stable stochastic system All right, and you took measurements of it. So if you like stacked up a bunch of measurements like you did with an autoregressive process from a stable stochastic process, from a stable system, like then the result that you get is L mixing. So that's what makes this powerful. So it's closed under a lot of operations. Like you can do a lot of things with your data. If you take a sequence and transform it in a bunch of terrible different ways, if the original sequence was L mixing, what you get out is still L mixing. So as a result is you can take a bunch of measurements from a stochastic process and you could stack them up like we did for the autoregressive process. Just to give you a reminder here, if these were generated by a stable system, this process, the joint process between this and this is L mixing. And so that means that we can apply all of the theory that we're going to talk about for system identification, at least this particular type of system identification. So, right. And then we have to have this condition just that it is Lipschitz continuous in both the theta and the z. That's just a special type of strong version of continuity. And so then the main theorem here, stated more precisely, is just what we saw before. The Wasserstein bound is bounded by this piece that decreases exponentially, and then this piece that grows logarithmically, and then of course there's all these ways to go and then tune these step sizes to get the various kinds of bounds we want. So just kind of quickly, I'm going to go over actually, the proof idea, because this is going to say why this is going to kind of get to the point of why this is not the same thing and why putting the constraints on it is actually pretty difficult. Okay, so my proof methodology in outline follows the standard proof methodologies that people use for the unconstrained things. So but some of the steps are different and more challenging, and I'll say why. So we've got our algorithm. This is just a different way of writing down our algorithm, and we're going to embed this into continuous time by just essentially sampling zero order holds. So we're going to embed it into continuous time using zero order holds, and what we're going to have right here is a continuous time approximation. And so if we just had this piece, and this piece, this would be what's called a stochastic differential equation, standard stochastic differential equation that you might see in the math department. And this is an extra piece that's called a reflection term that does not show up in standard stochastic differential equations. So if you didn't have this projection, you wouldn't have this extra piece. Okay, that's a reflection term, and you'd be working purely with stochastic differential equations. All right, and then the process that you go through is you say, okay, well, I'm going to bound the difference between the algorithm and this particular continuous time approximation. And then this continuous time approximation says, okay, I'm going to go everywhere I see this function, I'm going to average out the data. All right, so this is continuous time approximation with the data in there. This is continuous time approximation with the data out of there. And so we get three terms here, which is to say, this is the error that we get due to the just discretization, how we approximate this thing by continuous time. This is the error due to averaging. And then this is a continuous time process. Now, this is a continuous time process with no data, and you can show that that thing converges to that Gibbs distribution that we talked about before. All right, and so the challenge here is that the classical theory didn't have these reflection terms because it didn't have this, and it no longer is a standard stochastic differential equation. So what we have is what's called a reflected stochastic differential equation, which are much less studied. So when in general, if we had a system that looked like this, an update rule that looked like this, for any of you who've taken a class with me, you've probably seen the Euler rule. I know you've seen the Euler rule because you're in class with me, right? And so what happens is this is exactly an Euler step with just a projection. So it's a way of discretizing a stochastic differential equation. And in particular, as the dynamics, as the step size goes to zero, oh no, it's flying away from me. Yeah, as the step size go to zero, what this term here, this little funny looking piece that is just kind of written in this abstract way, this is actually capturing the piece, this non-smooth term that forces you to stay within the boundary. Okay, and so that adds some non-smoothness to the stochastic differential equation that's not there and makes it a fundamentally different object. Okay, and so that's why the analysis is different, because all of the previous analysis was built upon, in particular, a stability theory for stochastic differential equations. This is based on a stability theory for these kind of constrained stochastic differential equations. And so the main sort of result that we have in here, sort of the hardest piece of this paper, was really about showing that even with that non-smoothness, you still get nice stability properties. And in particular, what we showed was that if you take any two instantiations of this continuous time process and you run them forward, their distributions converge together exponentially. And so what that means in particular, if you had one that was starting at that Gibbs distribution, it turns out is invariant, so it just stays there forever, then it stays there at the final version, and you start here and you converge to that exponential. So let me give you, well, again, there would have been a video showing this where I showed two simulations. So let me show you what this would have looked like, okay? You would have seen this one going, and eventually they would have hit. So the proof method that we have for this is that essentially we have what's called a coupling method. And what we do is we take two instantiations of this stochastic process and we have them be identically distributed. But as we recall here, these are driven by noise. We're going to take two copies of that noise and we're going to make them identically distributed, but correlated in a very careful way to make sure that no matter where we started from here, these two would be rattling around and at some point they'd always hit. Okay, we can construct the noise to guarantee that any two processes would hit eventually. And you could use that, and essentially the way the proof works is we bound how long it takes for these processes to hit, and we can use that to essentially bound how close their distributions are. Is essentially the bit of trickery that we did in this, we meaning I in this particular case. The royal we, right? So yeah, so it's basically you got these two things, and in general, if you just kind of let them run, if you let two stochastic processes run, even if they're stable, they're not going to hit. But we cooked up the noise in a very specific way to make them hit, and then bounded how long it takes them to hit, and then using that, we could actually figure out how close their distributions are. And interestingly enough, and this is not like a great figure from what this paper was, we can extend all that analysis, and this is what I'm saying. We talked about things on bounded sets like boxes and balls, but this same contraction analysis, I work with my other student, Tyler Lekang, we showed how to extend that contraction analysis to much more general things, not just Langevin methods and not just bounded things, but any convex set. And we showed how you could use that to actually analyze the stability of adaptive control methods for stochastic systems. So based on that, I'm pretty sure that I can get this to work for any convex set, not just bounded ones. And finally, just very quickly, we're talking about averaging out the data variables. So the key insight here is essentially what we can do here is we can re-express all those processes, not in differential form, but in integral form. And what ends up happening here is this, if you kind of squint and take many steps back, this looks a lot like a concentration bound that comes from sort of standard, if you looked at like averaging independent identically distributed variables and you get what are called concentration inequalities on this. This looks really similar to the kinds of things you derive from those, but it's in particular a variation of that methodology applied to stochastic processes. And in particular, it allows us to say, hey, look, I'm integrating this thing from 0 to t. So if this thing were bounded, right, in principle, this thing could be as big as t. But it turns out that the L mixing property allows us to show that, hey, the effect of this actually averages out enough that this thing on average gives us an effect of at most square root 2, so much smaller than the actual time that we're looking at. And then by a bunch of manipulation, we're able to give a bound on this quantity. Basically, the continuous time with the data variables and the continuous time with the data variables averaged out, we can get a nice bound on those. All right. So that's that piece. There's a non-asymptotic convergence for projected stochastic gradient methods, and we can do non-convex losses, but convex constraints. And you could do this for a bunch of things like sampling, learning, identification, and so on. This, I am nearly sure, works on non-convex spaces. I have done a bunch of simulations and showed that it did, but I've not proved it. It also works for other methods, like second-order versions of this, what's called Hamiltonian Monte Carlo, if you might have seen it. All of these things extend in a very natural way, where instead of projection, you actually get, you simulate something like a bounce off the constraint set, like a bouncing ball. In particular, elastic collisions give you the right thing. And then there's other variations of enforcing constraints that we could deal with. So before I move on to the next part of the talk, does anybody have any questions on this? Yeah.
Some point way back then, you introduced non-smoothness to your system.
Yes.
And so the smoothness is still continuous, but you may just have a jump. Is that what you're doing?
Well, no. So the non-smoothness really comes from, I mean, technically, so if we go back to here, the non-smoothness comes from what happens at the boundary. Okay. And so actually, if you really kind of get technical, the piece is already not smooth because a Brownian motion is not smooth, but it is like more not smooth when you do that hard projection into the boundary. And in particular, it loses what's called a martingale property, like what you have over here. This is not a martingale. And so then a lot of the analytic techniques that are done for classical stochastic differential equations fail to hold, essentially because this, in some sense, you can think about what's going on when you do a projection. You have to look, did that send me out of the set? And that involves sort of looking into the future in some way. So that's actually technically what actually makes it more difficult, is that enforcing the projection requires peeking into the future slightly. And so then that's why it's actually pretty fun. That's the actual reason why it's fundamentally non-different. But in terms of looking at it, you can see that there's this really hard constraint behavior at the boundary where it just like hits. And a standard differential equation would kind of wiggle around, but it would never just like stop, whereas this stops. Yeah. Other questions? All right, let's rock and roll. Let's do the next one. Okay. All right, so this time this is a work from I guess about a year ago now on how to learn to stabilize systems without finding a model. All right, so let's talk a little bit about this. Again, there would have been a video here. It would have showed this thing flying up, going to the bottom and flying up, but that's not what it shows. So just to kind of take us a little bit of a step back here, this is all going to be about reinforcement learning, and as we'll kind of discuss, reinforcement learning is just kind of an extension of optimal control. So I want to first describe what optimal control is. So what optimal control is essentially you've got some task that you want to do. In this case, it was taking a pendulum that started off at the bottom, and you want to derive forces into you want to put forces into the pendulum to make it swing up to the top. So you want to put forces onto the cart to make this thing swing up to the top. So that's a really classic problem in optimal control and reinforcement learning. And so then you would put a cost function that says like, hey, I got low cost when I'm up at the top, I got high cost when I'm up at the bottom. Optimization algorithm, figure out what to do to make me get to the top. Basically figure out how to minimize that cost, which minimizing that cost involves bringing the thing to the top. And so we use optimization to go and find out a sequence of inputs that optimize this particular cost. And we're usually actually using a physical model of the system when we do this. So like if you do this for vehicles or robots, you use the dynamical model you have to help you design the system or design the inputs that you've got. And again, you would have had a video here, but we don't. So reinforcement learning is just like optimal control, except we don't assume we know the model. So we don't know the cost function, like we don't have an explicit representation of the cost function, and we don't have like a model of the physical dynamics of the system. So we got to learn how to do the control just from our experience, just from observing what we put into the system, the states of the system, and what losses or rewards that we get. All right, so that's reinforcement learning in a nutshell. Now, to present my work, I do need to kind of go into a little bit more detail about some of the categories and classifications of reinforcement learning algorithms. So there's model-based and model-free algorithms. So model-based algorithms do the following thing. They identify a model of the system, just using the data, kind of using maybe the regression techniques we saw in the last part of the talk. And then they use control. And they'll just use like, methods from model-based control to design a controller. That's model-based. That's model-based reinforcement learning, because you're learning the model and then using that model to control. And model-free reinforcement learning is you try to learn a controller without ever actually going through that intermediate step of learning a model of the dynamics. So you try to learn essentially what controllers lead to what outcomes in terms of like what controllers lead to good losses. That's what you're really trying to learn. And then there's two more distinctions that I want to deal with. One is the on policy case and one is the off policy case. So people who have done reinforcement learning might have seen these terms like SARSA and Q-learning. SARSA is an example of an on policy method where we learn essentially about what losses our particular controller that we're using right now gives us. And then, so we learn from the particular controller we're using, and then we figure out how to go and tune the performance of that controller to improve yourself. Now, off policy methods like Q-learning, you could do something very different and, in my opinion, kind of surprising, which is that you could just watch basically any controller, as long as it has this sort of sufficient excitation property, you can watch the behavior of any system. And from that, you could extract the optimal controller. So that would be like saying, okay, you just like watch me drive around at random for like, a couple of weeks. And from that, you build like, the optimal map to every Arby's in the city or something like that. That would be, something that Q-learning would allow you to do. You're watching some controller that is possibly very suboptimal, but you're still able to extract the optimal behavior, optimal controller from those observations. And so this work is going to focus on model-free off-policy method. All right. And in particular, we're going to talk about the absolute simplest optimal control problem, which is the linear quadratic regulator. And so in classical optimal control, so what we're trying to do here is this is a linear dynamic system. So this is a physical model here of very simple physics. And this is a quadratic cost function that we have here. And when all these things are known, this is an extremely classical problem, a lot of well-known solutions to it. And it's the easiest optimal control problem there is. So it's been known forever. All right. And, and MATLAB has a good implementation of how to compute this and so on. But once we get into the reinforcement learning world, where these things are not known, the theory on like how to actually understand this, like how many samples do we need to get good behavior from this, is surprisingly new. Like only in the last like maybe 4 years or so do people really start understanding even this simple of a problem from a learning perspective. And then, and even with that, there's still a lot of gaps in our understanding, and we're going to get to what those gaps are, because otherwise I wouldn't be talking to you if there weren't some gaps in our understanding of this. And one thing I really need to mention here is that between, I talked about how close optimal control is and reinforcement learning are, but for a long time, there had been this elephant in the room anytime somebody brought up reinforcement learning. And that is because, most classical reinforcement learning algorithms were defined for these finite state systems. And a finite state system, nothing too crazy can happen. A finite state system cannot blow up to infinity because there's no infinity in a finite state system. And in particular, there's no instability. So what instability is, sort of intuitively, it's just kind of like massive deviation from our desired behavior. It has a formal definition in terms of like the size of the states blowing up to infinity and so on, right? This would be an unstable linear system, the behavior of an unstable linear system. It blows up to infinity. This would be the stable behavior of a linear system. And within controls, so within the controls world, this is often like the main requirement. When you're designing a controller, like that's like the first thing that you ask, like, is it stable? You know, sometimes it's like the only thing people care about, or like really the primary thing that people care about. And the issue here is that the classical methods for reinforcement learning were defined for these systems where instability just couldn't happen. You couldn't fly off to infinity because there is no infinity. It's a bounded state system. And so, so now some of the methods for continuous reinforcement learning of continuous systems do ensure stability. Most do not. And for a long time, this was the case. You talk about, you know, you tell a controls person, oh yeah, I'm using reinforcement learning. And the first thing they say, well, does it guarantee stability? And then you say, no. And then they say, well, come back to me when it does. You know, this is like the conversation that I would like literally have with control theorists a few years ago. I mean, and I am one, but you know, I would have this exact conversation with people pretty often. And so this is the setup that we've got here. We've got a linear quadratic regulator problem. We're going to assume these are positive definite, but we don't know them. And we're just going to have a fixed collection of samples. So these samples are how the system moves from a current state, current action to the next state, and what costs that gave us to. And we don't know if we could actually find a way to actually stabilize the system, make it not blow up, make its behavior not go to infinity. And we definitely don't know that we don't know ahead of time if there's a stabilizing controller. So that's an important distinction, and that's sort of what the contribution of this work really amounts to. So when you have a model-based thing, it turns out that like, maybe let me preface this. I'm not saying that I'm like solving the deepest thing in the world. I literally came up with this when I was trying to make a homework set for my reinforcement learning class 2 years ago. And then I was like, oh yeah, we could probably do model-free stabilization this way. So like, this is not like, I'm not trying to say I'm solving something super deep. I'll just say that. The last one before that was actually kind of deep. This is not too deep. Okay, just let me just preface it with that. All right, so because I really do need to mention that like, hey, look, if you were going to use a model, this is super easy. You just go and like, you look at your data and you can just solve for A, B, Q, R, and then do real QR. It's super easy. So we're going to focus on the model-free method, which that hadn't been done. And in particular, there was a lot of works exactly on this problem where they needed to assume, if they're going to do a model-free method, they need to assume that they're starting with a stabilizing controller. Okay. So there's a lot of work on model-free control of linear systems, but they all assume that you have a stabilizing controller to start with. But as we talked about before, like from a control theorist perspective, stabilization is many times more valuable than solving this optimization. The optimization is like fine tuning at the end, and you might not even care. A lot of times you just use the LQR to get a stabilizing controller, and the Q and R are just, you know, some tuning parameters. But yeah, all of the previous existing work that does model free needed to assume that you had an initial stabilizer. So I was just trying to fill that little gap. And another little piece to keep in mind is that what we'll see is this is a fully off policy method. And what I mean by that is I'll be able to just have a collection of samples defined ahead of time, just like a certain number of samples. And if they satisfy one property, persistence of excitation, we can find a stabilizing controller and an optimal controller from that in a fully model-free way. All right, so before I get to that, I need to set up one more extra problem, which is the discounted problem. If any of you have done reinforcement learning before, you've probably seen temporal discounting, where essentially what this discount factor is this is telling you how much you want to weight the future. So when this gamma is less than 1, it says, I don't really care what happens in the future. You know, if the gamma is like 1/2, then like 10 steps into the future, you don't care about anything. You know, if the gamma is like 0.9, maybe you care up to like 60 steps or something like that. And so we're going to kind of come back and forth between, before I talk about this later, one of the most important sort of functions that we have when we do reinforcement learning is called the Q function. That's where the term Q learning comes from. It's called the action value function, and it has the interpretation as follows. So Q, K gamma, would be the cost that you attain if you started off at this particular state action pair, and then all points in the future you followed a particular game. Okay, so that is essentially, that is the value you would attain if from you start at x and q, x and u, and then from that point forward, you just use this very particular gain from that point forward. And so it turns out that, and this is a lemma, this is not a hard lemma, it's from a paper that I described, that that this system is this matrix is stable. A stable matrix in linear systems theory means all its eigenvalues are within the unit circle. All right, it's stable if and only if this Q matrix is finite everywhere. And in particular, it is defined by this matrix equation, which is called a linear Lyapunov equation. It's one variation of the Lyapunov equation, a somewhat non-standard one. All right, cool. So that is the Q function. It exists. It's defined by a Lyapunov function, Lyapunov equation. So there's a classic method from 1994 that does Q-learning for this. So the Q-learning algorithm in this particular problem, it generates that data that we talked about, generates the current state, current action, next state, reward or loss, generates a bunch of pairs, sets up an equation that looks like this to estimate the Q, solves that equation via least squares, and then it goes and updates the gain using just a formula based on how it estimated this Q matrix. And in that original work, they assumed that you have to have an initial stabilizing controller. There have been claims in the literature, including in pretty famous textbooks, that you don't need this to be stabilizing. That is false. I have counterexamples to that. It's wrong. And that's where this work comes in, because that's false. You can't just use this algorithm and have it work. All right. So the main, sort of the key insight here that kind of makes all of this work is that if your data is what's called persistently exciting, then that Q function that you estimate from least squares is actually exact. So in the previous paper by this, they said, oh, if you let the data go to infinity, it'll approach the exact thing, but it's stronger than that. You have a finite collection of data such that if you took all the x's and the u's, you stack them up as all the quadratic monomials, so like x1 squared, x1, x2, x2 squared, and so on, all the combinations of quadratics, all the quadratic monomials here. You let this be that. You stack this up into a matrix. If that matrix has full column rank, then that least squares problem for estimating the Q that I mentioned before is actually exact. And it's just like always exact. And so that actually tells you that what you can actually show from this is that this Q-learning algorithm proposed by that paper from the 90s is exact policy iteration. So those of you who've done reinforcement learning, it's the exact policy iteration algorithm. And so you will get to the optimal solution actually exponentially quickly. And notice here, this is just a fixed data set. So you can do policy iteration directly on that data set and it's exact. Yep. So you can get the optimal solution. And so yeah, I just briefly mentioned it that, essentially what happens is that you could do that policy iteration, but it's only sensible in the case that the system that you're looking at is stable in an appropriate sense. And essentially the original claim that that you could start your policy iteration with an unstable thing actually can fail. So there are regimes where you start with an unstable system and it'll become stable, but then there are also regimes where it doesn't work. So the final sort of insight that makes this all kind of put together here is that, hey, look, we got this discount factor. Remember, we say if this thing is stable, then that policy iteration that we have, Q-learning equals policy iteration, and it gets the optimal solution if we start with an initially stable thing. Stable just means all the eigenvalues are within the unit circle. So that tells me that, no matter where I start, if I make this gamma really small, that's just going to scale all the eigenvalues down. So any starting position I have, I can make the gamma sufficiently small so that I have the thing stable, and then I can run Q-learning on that. I can run Q-learning directly on my data set from there. And so in particular, trivially, if I multiply it by 0, it's stable because all the eigenvalues are 0 in that point. So then all I do here is just alternate by improving the gain by policy iteration and then increasing this discount factor. And you can show that that actually does converge to the optimal solution if it can be stabilized. So that is the main result that I have here. So this is just more formally saying what I said over there. And yeah, that's the theorem saying that, it will, It will stabilize it within a finite number of steps, and then it'll converge rapidly to the optimal gain. All right, just in the interest of keeping us on time, I'm just going to kind of jump to the end and say, yeah, hey, look, we've got this model-free off-policy method that just works on a fixed data set. We can use it without ever finding a finding a model to compute a stabilizing controller and then get the optimal gain with it. And the main actual trick there is this kind of twiddling between improving your gain and then increasing the discount factor until you hit 1. And it's probably possible to do the stochastic case, but I haven't done that. Yeah, so questions? Yeah. Okay, yeah, I thought it's all good. Yeah.
So thank you for the presentation there. Do you have a place where we can watch the videos?
Yeah, I could just I can like upload them, or like, is there a place you'd like me to like email them, or I can put them on my website? That would be, yeah, that'd probably be the easiest thing. Like, you know, my website's really crappy and not updated. It'd probably be better if I just emailed them, because I wouldn't know where to put them on the website. Is there a place I could email them? I could just email to like the class or something like that. I'll email you them, and then yeah, or I'll share a Google Drive or something like that. Yeah, I can share the whole talk with the videos embedded, and you know, and the videos themselves. Yeah. Yeah. Yes.
So if there were an optimal solution to cause system instability, what would just turn
So
the most optimal solution?
yeah, so here's what happens. So this is a really good question, and this is a subtle point. So what ends up happening here is that, remember when we're doing this discount factor, we're always kind of taking that discount factor and taking it as something that multiplied the cost and then transforming it into something that multiplied the state matrices. All right. Now, when this gamma is sufficiently small, this is always stable. Okay. And if this thing is not stabilizable, there is a number that is the smallest number so that you can't stabilize the system. And what's going to happen is that thing is just going to keep increasing, and it's going to slowly increase until it approaches that. Unmute. Yeah, somehow.
I don't know if you, there was a loop, but is the microphone pack still on?
I don't know. Maybe I bumped it. No, I think I bumped it.
Oh, okay.
Yeah. There we are. All right. Sorry about that. Must have. Yeah. So I mean, I haven't really tested it on anything big, so I don't really know. I mean, it's for small things. It doesn't take long, but it's definitely not as fast as say running LQR. Right. It's a lot slower than that. But I don't have a good sense of the runtime. It's not as, like I said, this is not like meant to be a super practical algorithm. This is more of a theoretical, like, oh yeah, people didn't know how to do this. Let's fill that gap sort of deal. Yeah, but they're not great. I don't have a good analysis of that. All right.
Other questions?
Well,
There doesn't look to be any questions online.
all right.
Nikos, did you have anything else left to say?
No, I wanted to say a big thank you.
You're welcome.
Very exciting stuff.
Thanks.
In fact, I had the most requests for the recording of this talk than any other talk.
Oh, wow. That's great. Thank you. It's good to hear.
So thank you, and have everybody a great weekend.
Yes. Thanks.